Alright folks, welcome back. In 4.1 we looked at combining functions graphically. In 4.2 today we're going to be looking at algebraically combining some functions. So we're going to start off with some simple examples over here. In the first example we are working with two functions. One of them is a radical, one of them is a linear function. We want to start off by noting the domain and range of each function. So let's list them out. If you consider f of x, it's square root of x, so domain and range for f of x are going to be as follows. The domain of f of x is simply x is bigger than or equal to 0, and the range for f of x, if you have an idea of general shape of square root of x, we know that the range is y is bigger than or equal to 0. We know that from experience working with radical functions. Similarly, for g of x, we know that the domain is going to be all real numbers. It's a linear function, so x belongs to the set of all real numbers, and the range is also going to be all real numbers. Y belongs to the set of all real numbers. Now we look at them independently. Let's combine them. We're going to rewrite a new function called h of x, which is simply a subtraction of f of x and g of x. So our new function h of x is going to have the expression f of x, which is square root of x minus g of x, x minus 3. You can furthermore open up the brackets and end up with the following expression: h of x is equivalent to root x minus x plus 3. We now want to determine the domain and range of this new function h of x. Well, the domain is easy. We simply look at the function and we're trying to see if there's any extra restrictions added on there, and we know that this entire function now has a restriction from that radical sign over there. So we know the domain is going to be all real numbers except x has to be bigger than or equal to 0. For the range, we cannot determine the range just by looking at that function. So what we have to do instead, when you're working with the range of these combined functions, you actually have to graph them and try and figure out what the range is going to be. So here in Desmos I have already graphed that function and I will load it up. So here is the function in Desmos. When I look at the graph of that function, I find that this is going to have a maximum point at 0.25 and 3.25. So as a result, I know that the range of that function is going to be y values less than or equal to 3.25, such that y belongs to the set of real numbers. So this means y is all real numbers less than or equal to 3.25. Let's take a look at another combined function. This time we're going to look at the combined function p of x, which is a product of f of x and g of x. So first things first, the equation for p of x is going to be square root of x multiplied by x minus 3. I don't need to go ahead and open the brackets up. I can leave it the way it is. Looking at that function, I can write the domain and range again. So for the domain, again from this expression I know I have a restriction, x is bigger than or equal to 0. So that's going to be part of the domain. For the range, again, just by looking at it, I can't really tell, so it's important that I go ahead and create that graph. So let me go ahead and graph that function. So square root of x, and this time we'll put this in brackets. And then when we create it this time, square root of x times x minus 3, in fact. So let me change that to a minus. We end up getting this particular function right here. And you'll notice this function will have a minimum point at 1, negative 2. So I know that this particular function is going to have a range of y values bigger than or equal to negative 2. So y is bigger than or equal to negative 2. Y is belonging to the set of real numbers, and here x belongs to the set of real numbers. So we're just looking at the combination of functions. For domain, we can generally look at the equation. For the range, we have to specifically graph that function and test to see what its range is. Okay, you give the next example a try. We will compare answers in a couple of minutes. So pause the video give that a try. Alright, so now that you've had a chance to try this question, we can take a look at the answer. So right off the back, original function f of x, the domain is going to be simply x belongs to the set of all real numbers, and the range is y belongs to the set of all real numbers. For g of x, our domain is x belongs to the set of all real numbers, and the range is y is bigger than or equal to 0. We know that because g of x is absolute value of x. Our first combined function is h of x, which is f of x plus g of x. So for the equation of h of x, we're going to get x plus 2 plus absolute value of x. If I take a look at that function, again the domain is going to be x belongs to all real numbers. I don't see any specific restrictions that are added in there this time. For the range, I have to graph the function. Again, I've already done that on Desmos. You can do the same. If I see that graph, this is what the graph will look like. You'll notice this graph is going to have a minimum value of y equals 2 and all values bigger than that. So as a result, I can say the range is y is bigger than or equal to 2 and y belongs to the set of all real numbers. Similarly, our function p of x is going to have the equation f of x times g of x, which means you're going to get absolute value of x multiplied by x plus 2. Again, just by looking at that, I can pretty much guess that the domain is going to be all real numbers. And for the range, again, I have to look at the graph of that. So let me load that up. So this is what the function will end up looking like. It will have a domain of all real numbers as well as a range of all real numbers. So what we're trying to do with these examples is look at the properties of some combined functions. So one of the things I want to point out is the reason why I had the domain as all real numbers is because both my original functions f of x and g of x had a domain of all real numbers. The range, however, was changed because the combined function does not necessarily reflect the range of the original functions. So for the range, I have to graph the function and see what the shape of the new function is, the new combined function is. Similarly, also in the previous example, if I take a look at it, the domain of f of x was x is bigger than or equal to 0. The domain of g of x was all real numbers. So the combined domain has to satisfy both domains of the original function. So I had to take x bigger than or equal to 0 as the combined domain. For the range again, there's no way I would have figured it out. One of the ranges is y is bigger than or equal to 0, other is all real numbers, but the new range was something completely different. So for the range, we have to graph the functions. You can also graph the functions on your TI-83 or the TI-84. You just have to look for the maximum or minimum points on your graph, which you should be comfortable doing by now. So these were some examples where we are adding, subtracting, and multiplying a couple of functions. Our next example is going to tackle the idea of the quotient of a couple of different functions, multiple functions. So here we have f of x as square root of x and g of x as x minus 3 squared. So let's look at these examples. So for our original function f of x, the domain is simply x is bigger than or equal to 0, and range will be y is bigger than or equal to 0. And for our original function g of x, the domain will be x belongs to a set of all real numbers. It's a parabola, and the range will be y is bigger than or equal to 0. I know that because it's a parabola opening upwards with a vertex at 3, 0. So now that I have the original function, let's look at the function q of x, which is the quotient of f of x and g of x. So the equation of the function q of x is going to equal square root of x over x minus 3 squared. Now for this function q of x, we can write a domain. The domain of our new function q of x is actually going to have restrictions based on not only the original graphs, but also its own form. We'll notice that original domain f of x was x is bigger than 0, g of x was all real numbers, so we do have that x is bigger than or equal to 0 as part of our domain here. But because of the fact that we now have a denominator, we have an added restriction here. We know that x also cannot equal a value of 3. So we not only have to look at the original domains, we also have to look at the combined domain of our new function q of x. For the range, again, we have to just go ahead and graph this. So let's go ahead and graph that, and once you graph it, we will get the range. So let's plug this in and see what we get. I plug it into Desmos, and what I'm gonna get is this function over here, which has a vertical asymptote at x equals 3, and looks like the range is going to be y is bigger than or equal to 0, so I can go ahead and write that down. The range of this combined function is going to be y is bigger than or equal to 0. Again, the idea is the same. We have to look at the original functions and the combined functions for the domain, and the range we look at just by graphing. You give the next example a try. It's pretty straightforward. You're looking at those two functions. Pause the video, give that a try. We will compare answers in a brief moment. Okay, so for f of x, we have a domain of x is bigger than or equal to 0, and a range of y is bigger than or equal to 0. For g of x, we have a domain of x belongs to all real numbers, and a range of y belongs to all real numbers. Okay, q of x, combination of those two, f of x divided by g of x, and a new function is going to have the equation square root of x divided by x minus 2. If you look at our new function, we anticipate that the domain is going to be a combination of those two to begin, so it's going to be x is bigger than or equal to 0. We also know that because we have a restriction x cannot equal 2, that's going to factor into our domain x cannot equal to 2. For the range, we now have to look at the graph, so let's load up the graph here. Here is the graph of the function. Again, you'll notice the domain is x is bigger than or equal to 0. There is a vertical asymptote at x equals 2. So the range is going to equal y is bigger than or equal to 0, or y is less than or equal to 0. In fact, because of the point here y equals 0, the range is going to actually equal y belongs to all real numbers. In case you're wondering why we got y belongs to all real numbers, again, if you take a look at the graph, y is all values less than or equal to 0 for this portion of the graph, and y is all values bigger than or equal to 0 for the above portion of the graph. So as a result, the combined range is y belongs to all real numbers. Alright, now that we can combine functions, let's try and work backwards. Let's try and decompose some functions as well, which is going to lead to our next example, example 5. In this example, we have been given a function h of x. Our goal here is to separate this into three separate functions, f of x, g of x, and n of x, such that h of x is equal to f of x plus g of x and n of x. So let's take a look to see how we're going to tackle this problem. When we break up these functions into smaller parts, we want to make sure that the domain of each of these functions corresponds with the domain of the overall function. We don't want to add any more restriction. So one possible way we can break up that function h of x equals f of x, g of x, n of x, we can basically say let f of x equal x squared, let g of x equals negative 2x, and let n of x equal the constant 3. For each of those functions, our domain is all real numbers. As a result, the domain for this h of x is also all real numbers, and we haven't added any extra restrictions, so we can break up this function into those three parts, f of x, g of x, and n of x. Let's try the next one. We want to separate h of x into two smaller functions, f of x and g of x. So for this, we again start off with the function h of x. And let's see if we can break it up into two parts. So why don't I do this? X squared minus 2x plus 3. So let me make this f of x, and let me make this g of x. In fact, before I do that, I should rewrite this. I can rewrite this as x squared, take out a GCF of negative, and then in brackets 2x minus 3. Now I can break this as f of x, and break this as g of x. And as a result, the combination h of x is going to be f of x minus g of x. So I can say my two functions are f of x equals x squared and g of x equals 2x minus 3. Now when I subtract those functions, I end up with the function h of x, which is a combination of f of x and g of x. Again, the domain is satisfied. All real numbers here, all real numbers here, and all real numbers here. We haven't added any extra set of restrictions. We can also verify this answer graphically. We can graph both those functions separately and then a combination of those and match to make sure that our answer in fact does lead to the same graph. Let's have you try another easy example similar to the one that we just did. So go ahead, give that a try, and then compare answers. So this time I want to break up a function into 4 separate parts, but you'll notice right away original function only has 3 components. So in order for me to be able to break it up into 4 separate functions, I first need to make an adjustment and rewrite it as 4 separate functions. And all I have done is taken any one of the terms, I picked 5 of x, you can pick any term, and break it up into smaller components, combination of 3x and 2x. Now that I have 4 components, I can just assign them each a function. So f of x is 4, g of x is 3x, n of x is 2x, and m of x is 2x cubed. Add those up, and you'll end up with h of x. And each of these functions will have the exact same domain as h of x. I have to watch out for that. So here we were adding. Let's look at the part B, which is subtracting. We're looking at difference of 2 functions. Again, same idea. Take your original function and break it down into 2 parts. Here I've done 4 plus 5x subtract a negative 2x. Once I break it up like that, I can assign f of x to 4 plus 5x and g of x to negative 2x cubed. So that way if I was going to subtract f of x and g of x, I would end up with h of x. If you want to look at verifying graphically, there is a good example on page 276 in your work text. You can refer to that, and they have shown a very nice method for you to be able to plug these functions into your graphing calculator and verify to make sure that you have broken them up properly. So both example 5 and 6, we were taking a look at breaking down functions by adding and subtracting smaller functions. In example 7 and 8, we're now going to break down functions into products and quotients of smaller functions. This is going to get a little bit more fun. So let's look at example 7 here. Here I've been given a function p of x equals x squared minus 2x minus 8. I want to write 2 separate functions f of x and g of x such that the product of f of x and g of x will give me p of x. If you think about what p of x really represents, p of x is a quadratic. You want to have 2 separate functions multiply to give you a quadratic. So if you think about it, all we really need to do is factor p of x. If we can factor p of x and get 2 separate parts, then those binomials will multiply to give me that trinomial. So I can rewrite p of x as 2 numbers that multiply to give me negative 8, add to give me negative 2. Well, my 2 factors are going to be x minus 4 and x plus 2. Now that I've got those, I can assign them values. This will be f of x, this will be g of x. As a result, I can say f of x equals x minus 4 and g of x equals x plus 2. Domain is all real numbers, domain is all real numbers, domain is all real numbers. I haven't changed anything. Let's try quotient. So now I want to find the quotient f of x over g of x such that the end result is q of x. So what's happening here? I took two separate functions, I divided them, and I ended up with q of x equals x minus 4. Since I ended up with a linear function, I can think of perhaps dividing a quadratic by another linear, which would result in a linear function. So let me write this down. A linear function is going to equal a quadratic divided by a linear. I could also do a cubic divided by a quadratic. This part is not that bad. The part that I have to watch out for is when I do this division, I have to make sure that I haven't added any new restrictions. So let's see what we would do over here. Let's say I said f of x is simply x minus 4 multiplied by another factor. And then g of x would simply have to be that factor. So when I divide f of x by g of x, then those two factors would cross off and you would be left with x minus 4. Now what you have to think about is, what is a possible factor that you can add such that when you divide them, there are no extra set of restrictions? If we had picked, say, the number x minus 2 and x minus 2, well, by doing that, we've just added a new restriction. We now have a restriction that x cannot equal positive 2. I can't do that, so I cannot use x minus 2 and x minus 2. Think about it. Think about it a bit more. Hopefully, you thought about something. And here's what you can do. We can use something like this, x squared plus 1 and x squared plus 1. Because the moment we multiply top and bottom by x squared plus 1 and x squared plus 1, I have no longer added any new set of restrictions, right? This thing is defined for all real numbers. That's defined for all real numbers. So I haven't added any extra set of restrictions, which means when I divide those two functions, I'm not going to have any bullet holes, I'm not going to have any asymptotes, and as a result, my domain of f of x and g of x is going to be the same as the domain of q of x. So this is one way we can separate those two functions into quotients. Actually, let me write that down over here. We cannot add extra restrictions when we divide two functions. And because I don't want to add any extra restriction is the reason why I chose x squared plus 1, x squared plus 1. In fact, x squared plus 2, x squared plus 3, x squared plus anything would have done the trick. Challenge for you, think of some other functions where you would have not had any extra set of restrictions. Let's have you give this a try. Example number 8. We'll finish off our notes. You give that a try and then come back and check your answer. So here is one possible solution for our last example here. We want to split up polynomial p of x equals x squared minus 9 into two functions f of x and g of x such that their product gives us x squared minus 9. Well, if I factor x squared minus 9, I get the factors x plus 3 and x minus 3. And I can make one of the factors f of x, the second factor g of x, and a product of those would give me x squared minus 9. Similarly for part B, I have the function q of x equals x plus 1. I want to split it up into two functions f of x and g of x so that their quotient is going to give me q of x. I started off with the factor of x plus 1, multiplied it by another factor that will not give me a restriction when I divide by it. So this time I use x squared plus 2, and a product of x plus 1 and x squared plus 2, the top part can become the function f of x. The bottom part, x squared plus 2, can become the function g of x. When I divide f of x and g of x, there is a common factor that will cross off, and you will have the function q of x equals x plus 1. There you have it. You can now go ahead and complete your homework. Good luck. Have fun.